Hello friends, welcome back. I Sumant Kadwane and I shall be explaining you memory interfacing in 8085 microprocessor. About the memory, memory is an important part of the microcomputer, and in 8085 the memory is the external element. Memory is made up of semiconductor materials which are used to store the programs and data in the form of instruction code. 8085 has a 16-bit address bus which is unidirectional and 8-bit data bus that is bidirectional. Now, the number of memory locations can be accessed by the address bus, which specifies the memory address. When we are using only one address bus bit, in that particular case we are able to identify only two memory locations. If we use two address bits, in that particular case we are able to address 2 to the power 2, that is 4 number of memory locations. In this way, if we go on increasing the number of address bits, in that particular case we are going to address more and more number of memory locations. But in case of 8085, the address bus is of 16 bits, therefore it can interface maximum of 2 to the power 16, that is nothing but 64 KB of memory size. We'll see further how this particular distribution we can access. Now in front of you shown one of the memory structure. The memory is basically, in case of 8085, starts from the starting address of 000 to FFFF if we are using the entire 64 kilobytes of the memory. But it is not necessary, it is depending on the application and the requirement of the designer. He can also use 1 KB, 4 KB, 8 KB and like that memory locations, and he can decide the starting address and end address of that particular memory location. For example, in this particular case, the address range of the EEPROM is from 0000 to 3FFFH. Okay, so in this way the designer can place the various RAMs and ROMs at the different memory locations, and accordingly he can design the chip select logic, and this particular determining the starting address, designing the chip select logic and designing the entire structure of the memory is called as memory interfacing in 8085. So let us see the table for the address lines required with respect to memory size. The number of address bits, address pins, if they are 10, then we can access the memory size of 2 to the power 10, that is nothing but 1K, which is 1024 bytes of memory. Similarly, if the number of address lines are 11, we can access 2K, 12, 4K, 13, 8K, 14, 16K, 15, 32K, and if it is 16 number of address lines, it is 24K, that is 65536 number of memory locations. Now, the size of the memory IC can be maximum 64K by 8, where 8 specifies you the data length. Now we are going to see what are the typical memory ICs require and what are the signals that are provided by the microprocessor to this particular memory IC. So first is the address bus. It depends on the size of the memory to be interfaced. For example, if you want to interface maximum of 64 KB, then the address lines required are 16, total 16. The control signals needed for static RAM are chip select, that is nothing but chip enable or CS bar. So this CS bar is nothing but the active low signal. When it is low, in that particular case the chip will be selected. If it is not, the chip it will not be selected. Next is the read control, that is output enable or RD bar. This is also active low signal, and write control WR bar. The control signals needed for read operation in EEPROM are chip select and read control, and we know that we don't write anything in read only memory, so WR bar is not needed in ROM, that is read only memory. Now in this figure typically shown the memory IC, what signals are required on the left hand side, and microprocessor provides certain signals, that is higher order address bus address lines A8 to A15, lower order address oblique data bus. They are multiplexed with each other with AD7 to AD0. ALE address latch enable, which is provided to the latch to demultiplex the address and data lines of the lower byte. Then IOM bar, it should be low in order to have the memory operation. RD bar and WR bar read and write signals, and ready, which may not be always shown in this particular operation, memory interfacing operation. So this is the typical structure of 8085 interfacing with the memory chip. In between we have shown the latch, so 8085 will always use this latch to demultiplex the higher and lower order address, and it is typically interfaced with the memory IC. Now it is up to the designer to design the proper chip select logic so that the chip will be selected right from the starting address to the ending address, which is required by the designer, and accordingly, so overall picture is shown in this particular slide, how we are going to interface the 8085 with the memory IC. Now let us start with the first problem of interfacing a random access memory 64K by 8 with 8085. Now this is the typical diagram shown for RAM IC with memory size of 64K by 8. The address lines required in this particular case are 2 to the power 16. So 2 to the power n is equal to 2 to the power 16. So n is varying from n is equal to 16. So it is varying from, address lines are varying from A0 to A15. Thereafter CS bar, WR bar, RD bar signals are required, and bidirectional data lines D0 to D7 are to be interfaced to the microprocessor. Let us see the address decoding table. This address decoding table will give you the idea about the starting address and end address of this particular memory IC. So because 16 number of address lines are required from A0 to A15, we have no option but to select the starting address as 0000H and the end address of 1111 all ones, that is FFFFH in case of hexadecimal numbers. Now let us see the entire diagram. So RD bar of 8085 is connected to the RD bar of the RAM IC. WR bar is connected to WR bar. IOM bar is connected to CS bar. So memory IC chip is selected only when it is a memory operation or IOM bar goes low. The address lines to be interfaced in this particular case are A0 to A15, and the data lines that are interfaced are D0 to D7, which is always there, that is nothing but 8 bits, 1 byte in this particular case. So this is the typical interfacing of 64K RAM with 8085 microprocessor. Now let us see the second problem. We have to interface 8 16K by 8 RAM IC with the 8085. Now the number of address lines required in this particular case is 2 to the power 3 into 2 to the power 10, that is nothing but 2 to the power 13. So n is equal to 13. Number of address lines required are 13, which are in this particular case A0 to A12, and number of data lines required are always 8. So typical structure of the RAM IC is shown in front of you, where address lines A0 to A12 are required, and other signals that are required are CS bar, WR bar, RD bar, and data bus has to be interfaced. The address decoding table for this RAM IC is shown here. Now in this case the starting address is from 0000H to 1FFFH. Therefore, the address pins A0 to A12 shall be used for address pins, and the remaining pins, that is A13, A14 and A15 of the address bus, will be used for the chip select design. The chip select design circuit is shown here. Whenever the IO M bar input output memory signal will become low, as well as this A15, A14 and A13 is 0, in that case that RAM IC should be selected, that is CS bar should be equal to 0. So one of the logic circuit for this chip select design is shown in front of you. Now in this case the bubbles are nothing but the NOT gates, and whenever we want that the input signal should be 0, we represent it in this manner. So for the NAND gate, whenever all the signals are 0, in that particular case CS bar will become low and RAM will be selected. Let us see the entire figure. Let us see this entire figure. Now in this particular case we have selected the chip select using the logic ICs, and RD bar and WR bar are connected. It is a random access memory, so both read and write are needed here. Address lines A0 to A15 are connected to the RAM, and 8-bit data lines D0 to D7 is also connected. Now the typical memory interfacing for 8x8 RAM IC is shown in this figure, and here we have shown the latch which is used to demultiplex the lower order address and data pins. And in this case the logic circuit is not shown, but it is shown in the earlier slide. So this is the overall picture of interfacing of the memory, and in this case the starting address will be from 0000H to 1FFH, as we have discussed earlier. Now let us see the chip select circuit using decoder IC. Now we can use the decoder IC 74LS138, and this particular IC will select a particular address, and accordingly it will provide you the output from Y0 to Y7. So whenever the address lines are, or whenever the input ABC across this particular decoder is 000, in that case Y0 is selected as shown in the chart. When it is 001, then Y1 is selected. When it is 010, in that case Y2 is selected, and so on. And when inputs ABC are 111, in that case Y7 is selected. Now most typically what we do, that the IO M bar signal we give it as enable signal, which is a active low signal in this case. So and E2 bar is connected to ground, and E3 is of course plus 5 volt. There are different notations for this for the various ICs. But this demultiplexer, or what we call it as decoder, not demultiplexer, this decoder is used for interfacing the various chips, and we can design a suitable chip select logic to select particular memory IC for the given range of address among the various memories. Now consider a system in which the available 64 KB memory space is equally divided between EEPROM and RAM. Now we have to interface the EEPROM and RAM with this 8085 processor, and we have to implement 32 KB memory capacity of EEPROM using single ICs. The number is also mentioned here, 27256. So in this case, let us assume the starting address for ROM as 000. So here we are connecting EEPROM first and thereafter RAM, or we can alternately do RAM first and thereafter EEPROM. So the address lines required for 32 KB are 15, that is 2 to the power 5, 2 to the power 10, which results into 2 to the power 15. So n is equal to 15, number of address line required are 15, A0 to A14, right? So whatever are the lines, data lines as well as the control signals that are to be interfaced to the RAM and EEPROM are shown you in front of in this particular figure. Next is the address decoding table. Now the number of lines that are directly connected to ICs are 15, that is A0 to A14. Let us consider that starting address of the RAM is 0000 and the final address will be 7FFF depending on 32 KB of size, and thereafter the EEPROM is connected. So EEPROM starting address is from 8000H and the end address will be FFFH. So the address pin A15 will be selected for chip select. So if A15 is 1, it selects RAM, and if A15 is 0, it will select the EEPROM. In this way, we can clearly specify the address decoding table, which is helpful for us if ICs are more than 2 and higher. This is the typical memory interfacing of 32K RAM and 32K EEPROM. Now, in case of RAM, since it is a random access memory, we don't use the WR bar signal. So WR bar active low write command is not given to RAM, and for EEPROM we have given the WR bar as well. So the signals that are connected to this RAM and is higher order address, lower order address pins, data lines, RD bar, and the signals that are connected to EEPROM are higher order address, lower order address, the read and write both commands, and this IO M bar signal will enable the chip select IC, and this A15 will be given as a chip select to the RAM. So if it is 0, then RAM is selected, and if it is 1, in that particular case EEPROM will be selected. The bubble is shown in front of CS bar of EEPROM in order to make that 1 to 0, that is nothing but a NOT gate, and in this way the memory interfacing of 32K RAM and 32K EEPROM can be materialized. Let us interface 2 KB of EEPROM and 1 KB of RAM with 8085. Assume the starting address for EEPROM is 0000H and RAM will be after EEPROM. So this particular figure shows you both RAM and RAM EEPROM and its corresponding interfaces. So for RAM, WR pin will be required, which is active low, but in case of EEPROM, this WR bar is not required. And in case of RAM, the number of address lines is 10, that is for 1K 2 to the power 10, so n is equal to 10, which is from A9 to A0. And the address lines for EEPROM are 11. So 11 is nothing but, in this case 2K, that is nothing but 2 to the power 1, 2 to the power 10, that is 2 to the power 11. So n is equal to 11, which is from A10 to A0. And the number of data lines in both cases are always 8. Address decoding table for interfacing of this 2K EEPROM and 1K RAM is shown in the figure. Now in this particular case, it is up to the designer how he selects the chip select logic, how he designs the chip select logic. But one thing we know, that the address range for this EEPROM is from A0 to A9, that is 00000 to this 11111. So it is in the range A0 to A10 in case of EEPROM. So what we'll do, that in second case the RAM address range is from A0 to A10, so 00000 to 11111. But now what is happening, that we have to use this EEPROM right from the starting address 000. So from 000 it will be having the end address 07FFH. Now the RAM is after EEPROM, therefore the next memory location will be 0800. So here A11 will be 1 in this particular case of the starting address, and that should be kept 1 in the end address as well, so that the range of the RAM will be from 800H to BFFH, right? And now it is up to the designer to select the chip select logic, right? So when the chip select signal should go low, when either these A12, A11 and A00 are either 0 or 1. When it should go 0 in case of RAM, when the A12, A11 and A10 signals are 2. So when from these pins it is either 0 or 1, EEPROM will be selected, and if it is 2, in that case RAM should be selected. And these are the ranges for the EEPROM and RAM. Let us see now how this can be materialized by using the decoder IC. And one more thing, that these pins, that is nothing but A13, A14 and A15 should all remain 0 all the time, and IOM bar should also be 0. So if it is materialized, then we can design the chip select logic and we can go for the memory interfacing diagram. Let us see the chip select circuit used with decoder IC 74LS138. Now, what thing is needed primarily, that A13, A14, A15 and IOM bar should all 0. So if they are 0, then only this particular encoder IC is enabled. Otherwise what will happen, it will not select, or it will disable this IC and the memory will not be selected. Now if A, B, C are all 0, Y0 will be selected. If it is 1, Y1 will be selected, and if it is 2, Y2 will be selected. But in case it is 0 and 1, we should have the chip select signal for EEPROM. That is why we have connected a AND gate over here. And if it is 2, in that particular case, we should select the chip select signal for RAM. So in this way we can design the chip select circuit. And now let us see the memory interface diagram using this particular chip select circuit. The memory interface diagram is shown in front of you. In this case, the chip select for EEPROM and chip select for RAM will come from the circuit which we have designed earlier using the decoder IC, and other things are almost the same. In case where it is EEPROM, WR signal will not be there, and when it is a random access memory RAM, in that case WR signal will be there. And this microprocessor will provide you the higher order address. ALE signal will go to this latch in order to demultiplex the lower order data and address pins, and thereafter RD bar, WR bar and IOM bar will go to the chip select circuit. So this is the overall memory interface diagram, and we can go for the design of various sizes of EEPROM and RAM if we follow this particular procedure. Now let us consider that we have to interface 8 KB memory ICs with 32 KB memory space, and we have to interface the 2 EEPROMs and 2 RAMs, and let us assume the starting address for EEPROM as 000. In both cases, for address lines required are 13, that is for 8 KB 2 to the power 3, 2 to the power 10, that is 2 to the power 13. So therefore number of address lines required are 13. Okay, so in this diagram you can see that what are the various signals that are required for EEPROM and what are the signals that are required for RAM. In case of EEPROM, WR signal will not be needed, but in case of RAM, WR and signal will be needed for the 2 RAMs. The address decoding table is shown in front of you. This number of address lines in this particular case of EEPROMs are 12. So from A0 to A11 the starting address will be from 0000 to 1FFF. Now we want that the next address of the EEPROM should be from 2000, and this is because this A13, A14 and A15 will be using it for chip select. Okay, so for chip select we will be using these signals, and when this is 0, in that particular case first EEPROM will be selected. When it is 1, in that particular case second EEPROM will be selected. When it is 2 decimal, in that particular case the RAM, first RAM will be selected, and when it is 3 decimal, in that particular case second RAM will be selected. Accordingly the starting address will from 000 to 1FFF, thereafter 2000 to 3FFF and 4000 to FFF. So therefore A0 to A1 and 2 they are directly connected to the memory IC, and A13 to A15 they are used as input to the decoder IC. Okay, so accordingly we can design the chip select logic. The chip select logic it can be designed using the decoder. So A13, A14, A15 will be used as input, and when it is 1, then chip select for first EEPROM will be selected. Therefore thereafter when it is 0, 1, 2 and 3, accordingly these EEPROMs and RAMs will be selected, and IOM bar will be used to give the enable or disable signal. So when it is memory related process, in that particular case these memories are selected, otherwise they are not selected, as we have seen in our earlier slides as well. This is the memory interface diagram. So 2 number of EEPROMs, for EEPROMs there is no WR bar that is connected, and for RAM WR bar is connected, and these chip select for EPROMs and chip select for RAM will come from the logic circuit which we have implemented earlier using the decoder. And once again, this latch is used to demultiplex the higher and lower order address and data bus. Lower order address and data bus, and IOM bar will once again go to that particular chip select logic. So here, in this way, we can proceed for either 4 number of EPROMs or 4 number of RAMs, and we can also connect 8 number of RAMs and EPROMs. Only thing, chip select logic will go on changing, and starting and end address will go on changing for each of these memory locations. So I hope that you must have. I must acknowledge the work of my teacher Dr. P.T. Karule, who is professor and head of the department Electronics Engineering at YCC, and who made me understand this particular subject and contributed me his PPTs as well. Now I should also acknowledge the book by Professor Ramesh Gaonkar with Microprocessor Architecture, Programming and Applications with 8085 by Penram Publication, and one more, that is nothing but Google search engine, which has helped me all the time in understanding every concept. Thank you so much.